Cool. Thank you very much. Thanks. So yeah, as our dear presenter said, that I'm from Zalando, and today I'm going to talk about my experience with working some projects that I have been involved last year, and it was about graphs, about data, about business impact, and all this kind of stuff. And I'm just going to share the experience with you. Okay. So, about me, I'm Giorgi Jvaridze. I'm originally from Georgia. I currently live in Dublin, in Ireland. And I work for Zalando, and I'm senior software engineer there. And Zalando, you might not know, or most of you probably don't know about it. I didn't know before I joined them, so it's fine. It's Europe's largest online fashion retailer. So we basically sell clothes online, and it's a German company. It's a German company. The HQ is in Berlin, but we have an office in Dublin where I work, and this office is focused on the data and data science mostly. Previously, I was a TripAdvisor. I used to work in a personalization team, so making recommender systems better, doing some NLP work there. And in parallel to my day work, I enjoy organizing events. I organize a Dublin Data Science meetup group in Dublin, and Data Science Tbilisi meetup group in Tbilisi, and Data Fest in Tbilisi as well. Cool. So this is kind of agenda, what I'm going to talk about today. Some intros about company, etc. Then I'm going to do some kind of refresher on graphs. I'm not sure how many of you know graphs, like how many of you did the CS course, and maybe you know about graphs from the university, maybe not. We can do some small refresher, right? And then I'm going to talk about the project, which is called Cross-Device Graph, and explain why it is, why we did it at all, and what was the value that it created, and then how like my team and myself created it, as well as some possible kind of how can you extend it further, and different approaches, and the challenges and conclusion. Cool. So Zalando, as I mentioned, German company. These are our three co-CEOs. I know it's not very usual to have three CEOs, but we have. And we want to connect people and fashion, right? So we want to make it easier for people to experience the fashion, right? These are some numbers. So we're doing pretty good in terms of revenue and numbers. And this is the like countries where we basically sell, where we operate, right? And you can see that Ireland, the country that I live, is recently joined to this list. So it was actually started this year. I also want to talk about the Data Fest. So one of my kind of hidden agendas here is to recruit people to come to my conference, as well as find speakers there. So yeah, so note the date, please. So 7-9 November this year. It's obviously a 3-day conference about data science, data engineering, as well as other data topics like data journalism, open data, like data in government, etc. And there's a website there, you can find more details. We did Data Fest last year as well, and we have around like 400 attendees, 40 speakers from different countries. You cannot see it there properly, but these are like numbers represent, yeah, they're numbers there, which represent speakers from those countries. So we had the pretty kind of high coverage of the international speakers. And it was really good, like we had really good feedback from both speakers and attendees. And we want to make it even better this year, so we're very excited, and I'll be really glad if anybody will join us there. Cool. Let's do some graph refreshments, like refresh our minds about graphs, right? So graphs are also called networks. So different kind of fields of science call it differently, and people are using the names interchangeably. So some might mix like words and that's very usual. But basically, networks or graphs are a collection of vertices, also called as nodes, or those on the picture it's represented as circles, and edges, which are also called as connections, and it's represented as a line, right? Yeah, so that's it. That's what a graph is. Of course, there are more nuances, there are more details, there are more types of graphs, etc. But the basic idea of graph is this, right? So some details. So graph, like connections between nodes, can have weight, right? So you can, if you are thinking about some real-world systems, you can think about, for instance, I don't know, pipe, like water pipes, and then how they connect to each other, and then you can think about how much water can pipe let through. So, and this is kind of a number that you encode in a weight of the edge, right? Yeah, so there's weighted and there's unweighted. So that's one kind of type of the graph. There's also direction concept in edge, right? You can have one-way connection or two-way connection, right? If you look at the colors there, you can visually instantly recognize or realize that like there's two different separate kind of mini graphs within the whole graph, right? And this is called connected components. So the connected components are parts of the graph that contains nodes that are connected to each other, but not to the other components. And this is important because we'll see in several slides. And each of the elements of the graph can have attribute. So like identifier or some, I don't know, some name or whatever, right? Yeah. And there are obviously many more algorithms and details about graphs that we're not going to cover now, but yeah, it's just a small refresher. Cool, so why graphs? Why we want to study graphs or why we want to use graphs at all? Well, first of all, in the real world, there are many kind of systems that are naturally represented as a graphs already. So you can see some examples like, like Facebook, right? So you have friends, and the person is you can represent the person as a node, and then connection, like friendship as a connection, right? And if you think about Twitter, for instance, in Twitter you can follow, but it doesn't necessarily mean that they also follow you. So in this way, the connections are directed. So you can think about arrows instead of lines. And there are other areas like biomedical networks, internet itself, right? All the computers are nodes, and then like network connections are connections, right? And all this means that lots of data science projects are also kind of can leverage graph theory and graph algorithms to process and deliver some real value to the business. And the project that I'm going to talk about is one of the examples there, right? Cool. So as I mentioned in Zalando Dublin, we are more focused on data science projects. It's called Fashion Insight Center. So we have many different teams that are focused on. Some of them are deep learning, images, whatever. Some of them are customer data. Some of them are product, like fashion item data. So there are many projects that we have. You can use imagination to kind of imagine what kind of projects we have, like recommender systems, fraud detection, all the stuff, right? And one of the big kind of subset of the projects that we have is based on the data that we collect from the tracking systems, right? So when you have a website, when you have some web application or mobile application or any application, basically, what you want to do is you want to make sure you understand your users so that you can improve the experience, right? And because of that, you are using tracking systems like Google Analytics or some third-party systems to collect all these insights. And when you do that, you might encounter different problems when you want to use this data in real-world applications. And one of the bigger problems is that your users are interacting to your systems from the different devices, right? So we all have multiple devices, mobile devices, tablets, laptops, whatever. And we are using, we might use same application from different devices, right? So we might use from mobile to just browse on the bus, and then go home and make a purchase. And we want to make sure that we understand the user kind of holistic way in order to make our data science projects kind of high quality, right? So if you don't ensure that data that you're putting in your model is good quality, then results won't be good. There's a popular saying that garbage in, garbage out. That's very true in this case. So in order to kind of solve this problem of users interacting with your systems from multiple different devices, there's a kind of industry solution called cross-device graph, right? And this is the kind of product that there are many companies that are doing it. Some of them are doing it internally for their own use. Some of them are doing it they're just companies that are built around this product, so they're just selling that by combining different data and building as a kind of cross-device graph. And that's what they have as a, you can purchase that from them, right? And two big players in this area obviously is Google and Facebook. But we are also doing it internally as well. And this is the project. So why or how are you going to use the cross-device graph, right? Or why do you want to build it? How many of you attended the talk previous to the lunch break? Shri, her name was, from Spotify. Can you show me hands, please? Okay, that's good. So I actually didn't know that she was going to talk about attribution. You see the first item there? So this is the attribution that she was talking about. And if for those of you who didn't attend, I'll do some fast kind of overview what it is. So when you're making advertisement to market your products on different systems, like I don't know, search engine advertisement or display advertisement or different advertisement systems or different types of ads, right? You want to make sure that you kind of measure what was the impact of your advertisement, right? Otherwise, you don't really know where to put money, right? Oh, hello. This is. Yeah. This is our automatic updater or something. Yeah, so you want to make sure you understand how your advertisements are performing. And in order to do that, you do the marketing attribution reporting, what she was talking about. And by its own, this attribution report has its own challenges, and she mentioned that, which are very complicated by its own. But also, the additional kind of challenge with the attribution reporting is that you want to have a holistic view of the customer. So if there is interaction to the advertisement from the mobile device and you don't know that this event belongs to the same, event of the, okay, let me say it differently. So imagine a person on a bus, right? And then they're browsing some application and they see the advertisement of some shoe or something, right? And then they go to home and then they make a purchase of this item. But the person wasn't logged in on the mobile phone. And when you're tracking this data, both on the phone and on the laptop, you don't necessarily know that this event and this event belongs to the same person. And if you don't know that, you cannot do this attribution. You cannot say that, okay, this advertisement was the cause of the, or not cause, but maybe influence to the decision that for them to make a purchase, right? And if you have this cross-device graph, you can kind of connect them together and then thus improve the report and kind of spend money more effectively on campaigns. So this is one use case, and this is major one. The second one is just other types of modeling, like a recommender system, for instance. If you want to build a like machine learning model, what you're doing? You are doing like data processing. You you collect all the data. You put it in a like training data mode or format. Like you have features, and then you have label. For instance, all the different details about the user, and then you have like label. Did they make the purchase or not, etc. So you shape your data so that your model can use it basically. And if when you're doing that, what you want to do is you want to, to make it very simple, you want to have like one row per customer, and then that will be like this customer's profile, and then you're modeling it, and you're kind of modeling your customer. The question is, how are you going to? What would be your identifier for this row, right? So, is it customer ID or cookie ID, or what kind of ID it is? If it's customer ID, it means that you are only modeling logged-in customers, which is not necessarily what you might want. So you can use the graph to make it better. I think I'm a bit behind time, so I'm going to make it a bit faster. And A/B testing. A/B testing is super important, especially in TripAdvisor. Every change was going through the A/B testing, even the features. And well, if it didn't kind of show that it improved users' experience by A/B testing results, we wouldn't publish it. Even the features that we thought that was really cool, and like everybody agreed that feature was cool, but users didn't like it, it wasn't going live. Okay. So I hope you're kind of convinced now how important this project is in terms of business value, right? Now let's talk about approach. There's two kind of directions. There's deterministic and there's probabilistic. Probabilistic is built on top of deterministic, so the deterministic is more simpler in a way. So let's start with deterministic. So imagine you have this table, and this table is from your tracking data, right? So you have some tracking data, maybe multiple tracking systems, and then you kind of build them bring them together. And each row here is an event, like, I don't know, like impression of advertisement, purchase, whatever. It's up to you, doesn't really matter. So what you do with this data is you extract the columns that are IDs, some kind of IDs, customer ID, device ID, cookie ID, other IDs. And then you put these IDs as circles here. And then you go through row by row, right? We go through the data row by row. And then when you see that two IDs belong to, are on the same row, it means that you know for sure that these two IDs belong to the same person, right? So what you do is you just connect them, right? And you do for this, and if you do for all of the rows, you will end up with this graph, right? And what you do next is you color them like this. And if you recall, it's called connected components algorithm, and you run this connected components algorithm, and the result is for each ID or for each node here, you end up with some kind of identifier. In this case, encoded as a color, right? So you can see there's like 3 different components, and we kind of think about these colors as a person or household, right? Maybe there's multiple persons but sharing computer, doesn't matter. And then we can kind of use this ID of the component as our base for all the different analysis. So this is a really simple kind of approach to kind of consolidate all the data together and represent it in a way that you can then use it in different systems. So this is the architecture. So on the left you see, so GAP is Google Analytics Premium, and others are our different tracking systems. So we get all the data from different tracking systems, different sources. We put them into the data lake. Well, data lake is like big kind of database kind of thing. And then we do kind of session processing, which basically means that we extract this, we take all the tracking data and we remove, or we only retain the ID values that we need, right? And then we construct graph. And then we kind of publish to the data storages that are more accessible to the other teams, other data scientists or engineers. Well, so the challenge in here is that on the scale of Zalando and similar companies, the data is really big. Like it's a terabyte, tens of terabytes, sometimes it might be up to petabytes. It depends how you represent data, etc. And the graph itself ends up in billion nodes. So it's like, it's not billion persons, it's just billion different IDs. And the reason is that some of the identifiers are very volatile, which means that they might kind of come and go fast, and then you end up with lots of different IDs. Well, the good news is that we are using Spark, right? And Spark is great. We all know that, and AWS is great as well. So this is kind of solving all our problems in a way. Cool. If you don't know about Spark, this is like one slide that shows how Spark works. So you have many computers, and there's one special machine called driver, or not machine, but process. You can see more proper to say it's a process, which is a driver, and then others are called executors. And driver is like master node. It kind of controls all the other nodes and makes sure that it doesn't kind of fail. And if it fails, then kind of restarts it. So it does all the coordination stuff, right? And then you have cluster manager on the bottom, which is managing all the physical machines like Yarn or Mesos or other stuff. There are many systems like that. Yeah. So and then there's algorithms. There's a way. So Spark is a framework that kind of enables you to work with this setup, right? If you do it manually, you can imagine how much trouble it is to kind of coordinate everything. So Spark just gives you a way to code your logic in a kind of nicer way. Cool. Yeah, and in Spark there's a library called GRAPHX. You probably have heard about RDDs and data frames. Even today there were a couple of talks about it. So as you know, RDDs are like base data structure of Spark, and then data frames are like built on top of it, and there's like optimization and all the different cool stuff in between. Similarly, there is a graph library in Spark which is called GRAPHX there on the second line, which is based on RDDs, and it's not very performant. Well, it's older system, so we shouldn't really use that. We should use graph frames, which is based on the data frames. Hence the name, right? Frames. Yeah, some properties about it. It's just 2 data frames. So the graph frame represents graph as 2 data frames. And one is vertices, and second one is edges. So vertices are nodes, circles. It's basically like file with where each line is a circle, right, or node. And edges are connections. It's a file with 2 columns, which represents from 2, and it means there's a connection from this ID to this ID. Cool. And in terms of code, this is like 3 lines, is basically what you need to compute these connected components or the colors on your graph data. As you can see, it's super simple. You have like vertices, you have edges, you kind of wrap it in a graph frames object, and call this function. Cool. So how do you compute the connected components? So if you think about connected components, what you end up with is that each node has ID, right, or color in the picture, in case of the picture. So the very naive implementation, which is implemented in GRAPHX, is when you assign random IDs to not random, but unique IDs to each node, and then iterate until convergence for each vertex, assign the component ID of the vertex assign the smallest component ID of the neighbor of the V to the V itself. So if you take a V, like some vertex, see the neighbors, just assign the minimum number. And if you do it over and over again until the convergence, you will end up with basically the connect components. Well, it's easy to implement and to understand. The problem is that convergence is slow, especially if you have some not regular graph with like big diameter. So you can imagine each step is kind of like doing one by one by one, if it's like one string kind of graph. So that's a problem. But the graph frames has implementation of this algorithm, which comes from this paper here. And it has this I don't know, nice algorithm, which is very simple as well. So you have these two steps, or two kind of processes, that you do until the convergence again. Small star and large star, right? And I'm not going to read this, I'm just going to show you the picture. This one. So on the left, you see kind of input graph, and this is the small star operation, right? And the blue one is the current vertex that we are currently processing. So the small star is the process where you connect all smaller neighbors and itself to the minimum of neighbors. So minimum of neighbors is 1, the green one, and then you connect smaller to 8 nodes, 5 and 7 and 8 itself, to the 1. This is one operation. And the second operation is called large star, which is connect all strictly larger neighbors to the mean neighbor, including self, right? So you do this operation. And if you're curious about why it works and how it works in more details, you can check this paper. But there's a theory that if you do it over and over again, it will work, and it will end up with the connected components, and the performance is log n, so it's very fast. Cool, and then again, that process will end up, you will end up with this kind of representation of connected components. Cool. Anybody has a question so far? Maybe everybody's, yeah? Sorry, can you repeat this?
In this table that you've shown, how you understand that IDs should be in one row or not in different rows?
So one row is the event. So if you have event,
yep.
For instance, person viewed advertisement or click somewhere, you know the tracking system. When you implement tracking system, you say, okay, I want to have this kind of events tracked. You know, it's up to you. But when it happens, you have different IDs in a context. So you have cookie ID, you have maybe device ID, you might have customer ID, and you will put all these IDs in this event. And if you do that, those 3 IDs will be represented as a kind of one row. Yeah?
Okay.
Cool. Cool. So this was the deterministic approach, right? So why is it called deterministic? Because there's no randomness involved at all. If you repeat this process over and over again, you will end up with the same result. But we can do better. Why? Because back to the question, we are only using the IDs, right? But we have so much more data. We know about products, like fashion items. We know that, how similar they are, how, I don't know, different fashion, I don't even know, different fashion terms that I don't fully understand, some, trends, etc., and behavior. So we have more data. So the idea is that we can use that data, that information, to improve our graph. So the question is, how do we do it? Yeah, so the example that I also briefly mentioned is that even if we never even if you have a situation where the user browses on the mobile and then makes a purchase on the desktop, and there's no kind of other events that they will connect together, we still kind of know, for instance, where the user is, right? We know the kind of geolocation, we know country, we know device type, we know what item they browsed. So if you think about it in that way, the two kind of disconnected events which have all these attributes, same, like same country, same product, etc., should have higher probability to belong to the same person than the random two ones, right? So there's some information in there. So we can utilize that. And way to do it, or one approach would be to do so-called the link prediction, which is kind of given the graph, you are calculating probabilities of all other possible connections or edges. And you can state this problem of prediction of the connections as a binary classification problem. And you can do it by if you have your deterministic graph, and you know the connections here, right? And you say, okay, these connections are my positive cases. So we know for sure this data, we have data, it is fact that this kind of, this event told us that these two IDs belong to the same person or household. So these are our positive cases. So if you're familiar with the binary classification machine learning problem, you have positive cases, negative cases. So this is positive cases. So where's the negative cases then? So negative cases are all the other possible links that we don't have, right? So if you take two random IDs and you see there's no link between them, it's kind of negative case. Here it's not, I drew some, with the red lines, I drew some of it. It's not all the possible pairs, as you probably can guess. But still, it's kind of some sample of the negative cases. And then when you do that, you can kind of represent this graph as a table again, and where you have, on the first column you have vertex 1 features, or node 1 features, and you have node 2 features. And I don't know if you know about the features are like all these attributes like geolocation, gender, product details, etc. And you have label. So in the green cases of green, you have positive or true, and in the case of negative, you have false. So, and then you just take it and put it in whatever binary classification algorithm you like, and then hope that it will produce better than kind of random guess. Cool. Yeah, so once you have it, then you might ask, what kind of features can I use for my algorithm? Because if you go back to the original kind of representation of the problem, we just have IDs. But we can also have, as I said, like product data, GeoIP data, etc. But we can also have other kind of data or features. So these are some ideas of the features that you might want to use. For instance, so ID metadata, like when was this ID first seen in all my historical data set, or last seen, or how many sessions this ID was involved in. Was it mobile, desktop, browser, all the different features. Product information, fashion information, like maybe trends. You can see if you can see that somehow that this ID is following this trend, this fashion trend, and also this ID is following this fashion trend. It might be that the case that they are the same person, so it's a kind of signal to that. In addition to that, you have in a graph you have neighbors. For each ID you have neighbors, so you can use the neighbors information. And you can also use more cooler stuff, like in a tech way, the features that are derived from some graph theoretical algorithms, like graph centrality scores, or community detection scores, or even the newer kind of cooler stuff that's called graph embeddings, which I'm going to talk about a bit now. So the idea of graph embeddings is similar to the other embeddings, which is, you probably know embeddings from images or text. The most popular one is probably Word2Vec, and also the convolutional neural networks for images and other stuff. So there's a kind of similar approach to the graphs, and you can read these links later if you want. Yeah, so the word2vec, if you don't know about word2vec, it's super popular kind of way to represent semantic meaning of the words by just just by putting the whole corpus of the data in this algorithm, and then you end up with a kind of vector representation of the word, which somehow encodes the meaning, semantic meaning. And you can see here, for instance, if you take this vector of each word and then kind of do dimensionality reduction, so if you have like 300 dimensional vectors and you represent it as a three-dimensional vector, you can create this kind of chart, right? So you can see like three-axis chart. And then when you plot some of the data points, you can see that on the first one, the man and woman and king and queen are kind of separated with the same vector. And the idea here is that this vector is representing kind of gender, right? And in the second case, it's a verb tense. And on the third case, it's a relationship between Spain and, not Spain, but country and capital. So this kind of shows that this algorithm of word2vec somehow learns this semantic relationship. Semantic as well as syntactic in the second case. And if you want to do something similar for the graphs, you have to do some transformation first. So idea is that the goal here is that you want to have a similar kind of vector for each ID or for each node. And then you can use this vector as a kind of feature for your machine learning algorithm, right? So if you don't know what's vector, it's like a bunch of numbers, right? So 300 numbers or 100 numbers. The amount of numbers doesn't really matter much, but it's just numbers. And then on this slide, on the feature, you see the vertex 1 features, you will have like a bunch of numbers there. And one of the numbers will be those embeddings numbers. And so if you want to use, so the idea of the node2vec is to do word2vec on graphs. But word2vec is designed for text. But what you can do is you can represent a graph as a text first, and then you just run a word2vec on that. And way you represent the graph as a text is via a thing called random walks. And the idea of the random walks is you pick random node, and then you go visit neighbor, you choose neighbor randomly, visit it, choose another neighbor randomly, visit it, etc. So in this case, it's not visible. Okay, so in this case, this kind of snippet of the text, in quotes, is generated from the process where we pick C1 node, then when we go to F1, and then we randomly decide to go to C2, and then U1, and then back to F1. So you can go back as well. So it's just random process. And then the second one is I don't know, U1, C2, etc. And then you do this randomly. You kind of do it like whatever many times you want. And then you take this text, put it in a word2vec, and then you end up for each word, or in this case, ID of the node with a vector. And the reason why this works is that in a text case, the theory or hypothesis is that your words are explained by its neighbors. So if you imagine a sentence and then you delete one word, you can kind of guess what this word might be, right? Better than random guess. And in graphs, it's a similar idea. You can kind of each node might be represented by its neighbors. So hence, it kind of there's a parallel there. Cool. Yeah. So that was it in terms of probabilistic approach. Yeah, it's a big topic. You can kind of improve it and kind of measure performance. You can probably do A/B testing to your graph, see which one is making your company more effective in some KPI, etc. But we have some challenges involved in when we're working with the big graphs. And the two big challenges are visualization and data quality. So this is a table which represents components ordered by number of IDs inside of components, or number of nodes. And you can see that, and it's sorted by number of IDs. So you can see that the first one is like 4 million almost. So the question is, why is it so big? We don't know. It's what data gave us, right? So we put data, everything is deterministic, there is no guessing, we just processed it in a way, and we ended up with this, right? So this is a problem. Why is it a problem? Because you know for sure that there is no one person with so many different IDs. So what's probably happening is that some kind of tracking bug or some kind of bot traffic on something is wrong with the data. And then it kind of makes different person identifiers to collapse and coalesce to the one big blob together. And again, the problem is here when if you don't kind of filter it out or fix this, you might end up with the problems like one person's activity might influence another's recommendation. You know, it might mess up your models basically. Cool. So one of the things that we tried to approach this problem to understand why is this so big was using one of the graph theoretical algorithms called betweenness centrality. Betweenness centrality is a way to calculate kind of bridginess of the node, how connector this node is. And in order to demonstrate this, I have this example graph, which is a very famous data set. It's from the Florentine family marriage network from 13th century, I guess, very old one. And you can see that there's a name of the family, and then the score on the right side is a betweenness centrality score. And you probably have heard Medici's. They were very influential. And it's kind of shown here that they have high score here. So it kind of encodes this influence in a numeric way. Intuitive understanding of the score is that, for instance, if you are like those guys on the bottom, I'm not going to try to pronounce them, and you want to connect with other people, you probably have better chance if you go through the Medici's, right? And technically, you can calculate the score by generating all possible shortest paths. So you just take all the pairs and then calculate shortest path between them. And when you have all the shortest paths generated, for each node you count how many shortest paths lay on this node basically. And more shortest paths lay on the node, it means that they're kind of good connectors. So the idea of using the betweenness centrality to investigate this big component is that so we want to find IDs that are some error, like mistake, something is wrong, yeah. So we thought that's a good approach, right? Yeah. So these guys have high score. Problem is that there are 4 million nodes, which means so many pairs of IDs, which means we cannot really do it. Well, we actually did it approximation, so you can actually sample nodes, and it kind of helps. But in practice, you cannot do full calculations. What else can we do about it? So there's this area of graph theory which is called partitioning, and the idea there is that you want to find a way to break the graph in a manner that it will minimize connections between the parts, right? And this is really, really well studied area because apparently it's been used in like chip design and some other old kind of scientific research. And there's this software called Metis, which you can use, and it's super efficiently implemented, and it works very fast. And the way it works, it kind of, you can see like arrow goes down and goes up here, right? So you have the original graph, then you do this process called coarsening, which is like making your graph simpler by doing some procedure. And then you coarsen it enough, and then you try to break it, and then you kind of build it up back, right? And it works well. It finds kind of like the kind of places where you want to break the graph, which is represented with green lines here. And the idea is here, like, I think about this as if you have like some object, like stone object or plate or something, and you drop it millions of times in parallel universes, you will end up with places where it will break in the same place, right? Because it's a weak point. Yeah, you should do it in parallel universes because plates should be same, right? Cool. Yeah, so you can just use this partitioning operation many times and see where it breaks, and then ideas that it will be in these bad spots, and then you can kind of explore these areas and see what's wrong there. Cool. Some other ideas. There is a community detection methods, which is it's like clustering in a way. There is also spectral clustering, which is clustering again. If you're familiar with K-means algorithm, it's basically applying K-means algorithm to the graph that's kind of laid out on a space. You can also use some visualization tools to explore the shape of the graph. But the problem is that if you do visualization, you will end up with this, which is not, yeah, it's not very nice here. It's better on my laptop, but anyway, it looks like stars and space, right? There's so many IDs that you cannot see anything. It's just a bunch of lines, and it's like, yeah. I mean, it looks great, and I use it on slides, and it's nice, but it's not useful. Except you see that there's some artifact on the left. There's something going on there, but you cannot really do anything with it. Yeah. So too big. Most of the tools that are designed for graphs, I don't know, maybe like Neo4j, iGraph, something. All the tools, none of them are designed for the scale that we are talking about here, with very, very few exceptions. Which means that if you just try to use it, it will just fail. It won't even open the application. Yeah. So another one is this hairball problem. They call hairball to the graph visualizations where you look at it and it's like a hairball. So it's just a bunch of, you don't understand anything there. It just looks like hair. Yeah, and the graph layout is slow as well. I was fortunate to find this open source project from this guy. It has this kind of JavaScript tools, which is very unusual, but unusual for this kind of big data tools to be written in JavaScript. But it's really nice. So it kind of handles big visualization of graphs. This picture was produced from one of his projects. And one other aspect of it is that if you have used any graph software, when you open it, it kind of starts to lay out, right? You see the animation there, like spring, it's called spring force algorithm. You open it and it starts to lay out. The problem with the graphs so big is that this layout is super slow. So one step takes, I don't know, many minutes. So you want to have this layout done offline. And this guy has the implementation for it. Cool, I'm almost done. There is this whole area of research called graph summarization, which studies the kind of approaches on how to handle big graphs. And in terms of, so there is a different kind of, what's the word? different reasons you want to do summarization, right? You want to, I don't know, study anomalies like we had the case, or you might want to just visualize it for some reason, or you might want to make your systems more efficient, like make your database faster, different reasons. And for these different reasons, there are different kind of approaches. And there's this paper, which is a survey paper, which means that it's a paper that describes all the other papers that talks about it. And I highly recommend it if you have the same situation, if you have big graphs. Cool. I'm done. As you see, I use this picture to kind of make my slides prettier. Thank you very much for listening, and I'm happy to answer your questions.
Yeah, guys, thank you. And we have time for several questions. Who would like to be the first? Okay, I see the first one.
Thank you, Giorgi. It was really cool. Just curious, did you have a chance to investigate root cause or root bug which leads to such huge component that you observe? Probably it would be like much easier to fix it or submit some kind of tracking issue to Google Analytics.
Yep.
Thank you.
Yeah, great question. I didn't mention, so I didn't say, but we found reasons. But there's no one reason, there are multiple reasons. And you find the reason, you fix it, it kind of shrinks, but it's still big. You find another one, it shrinks, find another one. So it's kind of, real world. That's how real world works, right? One of the reasons that we found, for instance, it was some developer decided to track null as a string, and then so one of the IDs was a hash, like MD5 of string, right? Because of privacy issues, etc. And as you know, when you have the hashes, all hashes look like each other. Like you cannot see which hash is correct, which is not correct. And we found that there was one hash which was MD5 of string null. Yeah, and there was like others like hash of 0, I don't know, all these different variations of test values. And the problem with these kind of values is that if there's a bug, and then like our mobile engineers or web engineers, they release the code, lots of traffic kind of agglomerates, I don't know this word. They kind of join them together because of that, and then that's a problem. In addition to that, we had bot traffic, so people want to check our prices, probably, competitors. They don't really follow our convention how to request our site, so they might use one value for all the requests, and then it just joins together. Also, there are some kind of browsers, especially in Germany. I haven't heard it before, but there's some kind of browser that intentionally puts bad data in the tracking systems, which is good in a way. I mean, it's but when you are dealing with the data yourself, it's really bad. So yeah, those were the most what we found.
Okay, so we have time for one quick question and one quick answer.
Can you give an example how you use results data at Zalando? Like, what do you do with all the graphs when you have them ready?
With graph data?
Yeah, when you visualize them,
yeah.
Like, what do you use it for?
So we don't use visualization. So visualization was our attempt to kind of increase the quality of it. The way we use it is so this table with the colors. Each color, you can imagine that instead of color that you have additional column, which is component ID. Okay, and then this is the product of my team, right? This is what we ship, and then there are other teams, for instance, recommender system teams, who have all the data, and they want to kind of they want to resolve all the data to which component they belong to. And then they would do like group by this component, so each row will be a component which is like a person or household, and then do whatever algorithm they want to do, recommender system, whatever.